Let me go ahead and start recording. I guess we have 8 people here, which is most people, but some people, I think we might have a few people that aren't here. Let me go back to sharing my screen. So we're just going back and going through problems that might appear on the exam. So just in case if you guys want to go over this again later too, it'll be on the video. So that way maybe you can go back through and hear us talking about which problems are good, which techniques are good, which things to know to help you guys study. So right now we're just looking at matrices of linear transformations. And I mentioned how 5.2, really important, 5.2.2 exercise, and how we determine the matrix of a linear transformation when we know how a matrix or how a transformation is acting on a set of vectors that may not be the standard bases. So follow up to from that problem, you see 5.2.3, 2.4, 5.2.5, all of these problems here. We're given information about how a transformation acts on a collection of vectors. That may or may not be a basis. These collection of vectors may or may not be linearly independent. And then we're given the result. And so what we're trying to do in each of these problems is find the matrix T. Probably going to have a problem like that on the midterm. It's a very standard problem. And then, so after that big chunk of problems, we've got kind of another chunk of problems down here. So if you look at 5.2.8 all the way up to, I guess there's only 2. Looks like it more, but there's only a couple here with a bunch of different parts. So these are good exercises in determining which types of transformations are linear and which ones aren't. So here we're not necessarily giving you the matrix of the transformation, but we've seen other forms of linear transformations where we simply describe how the transformation is going to act on the vector. So here we've got our vector x, y, z. T is going to be, send it to the vector x plus 2y plus 3z in our first coordinate, and the second coordinate 2y minus 3x plus z. So understanding why some of these can be modeled by a linear transformation. Namely, you may want to think, which of these can I actually write in terms of matrix multiplication? And which ones of these can we not write in terms of matrix multiplication? So these might make good true false questions, or at least a good short answer, explain why this may not be a linear transformation. Let's see. So here's a theoretical question, right? Suppose you know something that the inverse of exists, show that there always exists a linear transformation. That one may not be too bad. It's a theoretical one. I would know some general arguments behind something like that. And then these ones are also other types of linear transformations. So other than looking at combinations of the x's and y's, we have these projection transformations. So we actually did an example like that in the lecture. And projecting one vector onto another, we showed were linear transformations, and then came up with the matrix corresponding to that. So those are potentially fair game as well. So really only like 2 or 3 different types of problems in this section, right? Coming up with a matrix of a linear transformation, understanding which ones are and aren't, and then maybe some more exotic types of transformations like projections. Then we moved on, so we're talking about properties of transformations, and this section fairly short as well, at least by the way we were introducing it in lecture. We kind of skipped this, or I guess I mentioned this in class, but these are good to kind of pick out what is a linear transformation and not. And primarily like this first one, the first 2 bullets, we don't really need. They are results of this third one. This third one is the big one, the big defining notion of what is a linear transformation. This is how we defined our linear transformation, namely that it preserves linear combinations. And from this, you can actually deduce these other 2 points. However, keeping these other 2 points in mind, once you've kind of deduced them, they're good checks. Right? If we go back up to these problems and we want to know which is a linear transformation and which is not, they're good things to check, because if a transformation violates any of these dots, it's not a linear transformation, and that's a good justification. Primarily, like this first one's an easy one to check. Does the transformation send the 0 vector to the 0 vector? If it doesn't, it's not a linear transformation, and that's all you got to say. Not a linear transformation. T of 0 doesn't equal 0. or if it doesn't preserve negatives. T of negative x doesn't equal negative t of x. Not a linear transformation. So pretty quick justification using these types of bullets. Of course, if we actually need to do computations with this, the key thing, preserving linear transformation. So maybe an example like this might show up from this section, where we simply have now t acting on a pair of vectors. And maybe we don't have, that's not enough information to find the full matrix of t. But we can still find out how t acts on other vectors based on forming a linear combination on the information on the vectors that t does act on that we are given. So decent example there. I think there's other examples like that in the exercises. I think the only other thing from this section was this part here. Big thing, if you know matrices of linear transformations and if the dimensions work out correctly, we can always compose linear transformations, and then the composition of linear transformations corresponds to matrix multiplication. Probably be an easy question like that, or at least one where you got to just multiply two matrices together to compute the composition. So those are the two big things from this section. This question asks about T inverse. T inverse, of course, there's going to be inverses on this exam, but that'll probably, it ties more into the like kernels, images, one-to-ones, and isomorphisms. So kind of like the last exams, I guess I should say, you probably expect 7 or 8-ish questions. I think it's been a decent number. It didn't seem like it was too long last time. I gave you guys some extra time, but everyone was able to finish by like 1:30, which I think was good. So I'd like to keep it not longer than that by any means. So you can kind of expect there's going to be probably one question from each section at most, and then even less than that, because some sections might tie in. I can kind of tie in some of the concepts within one problem. So it may not be worth testing over different sections of problems when really one section, for example, like when we get to the matrix of linear transformation 2 and general solutions, once you know how to do those problems, it kind of makes these first few sections a little trivial. So there's no need to put a unique question from each of those. So some examples here from our properties of linear transformations. If a function is linear, then it is always case that t of 0 equals 0. So we know that as a property. Being able to demonstrate that, I don't know if I'll put something like that on the exam. We'll see. I think you guys, it's an easy demonstration, and it's actually in the book. It'll come up later if we keep scrolling. I might put it, I might not, but at least it's a good thing to know and kind of understand why linear transformations should preserve the 0 vector. And then it's an important tool. You can use it quickly to identify what is and isn't, or what isn't a transformation at least. So of course, if a vector, or if a transformation does preserve the 0 vector, doesn't necessarily mean that it's linear, but we can conclude that if it strictly doesn't preserve the 0 vector, we know that it's not linear. And you can see these problem sets. You're given a matrix, another matrix, find the matrix of compositions and find out how it acts on a vector. You know, matrix multiplication, and then another matrix multiplication by acting on the vector. You got a few of those types of problems here. Given a matrix, find the inverse. That you guys know how to do. Linear transformation acting on maybe a non-standard basis. This one has a couple parts. You might want to find the matrix itself, and then it asks to find the inverse. So of course, all that you know how to do. And of course, that's a multi-part problem. So anytime there's a multi-part problem where it's tying in different concepts, one, finding a matrix of from a non-standard basis, and finding an inverse, you know, it's going to kind of cover multiple sections of material a little bit there. Section 5.4, I would actually like to go over this a little bit again today. We briefly talked about it. So you should know the rotation matrix, and you should know the flip matrix for the flip over the x-axis. And then if we get to more of it today, there might be a few other questions. I haven't thought about like what types of questions I want to put on the exam from this section. I know I don't want to make them too hard, but if I don't make them too hard, it's almost like they're all going to be fairly easy. So maybe there just might be a couple easy questions as long as you know the ideas of this section. So you should know this matrix. This is our rotation counterclockwise by an angle theta of the plane. And then the other one we mentioned in class. And it's when through a reflection over the x-axis. And that's when m, the slope of the line, is 0. So if we have the x-axis, a line with a slope y equals 0, plug in m equals 0, and the matrix we found was 1, 0, 0, -1. So you should know at least that matrix. I think this one is going to be important to show. I gave that kind of as an exercise, as a homework problem. Maybe if we have time today, we'll go through that part of the exercise. The other thing that is, I think, pretty nice and pretty important from this section is, let's see, I might have scrolled past it, is this result here. You can actually derive the angle sum and addition formulas by matrix multiplication now. So if you understand that this matrix here is our rotation matrix, well, if I apply it, if I rotate by an angle theta and then rotate by an angle phi, say, it's going to be the same as rotating by the angle theta plus phi from the beginning. So that's a fairly important result. All those angle sum and angle difference formulas that you learned in pre-calc, you can actually now derive by transformations of the plane. So namely, if we have a rotation matrix where we're rotating through an angle of theta plus phi, well, you just plug in theta plus phi into your sines and cosines. But this should be the same as rotating by phi and then rotating by theta. And that is going to be given by matrix multiplication. And so if you multiply those two out, you can equate component to component, and you'll get the formulas for the angle sum formulas and angle difference if you'd like. So pretty important result there. Maybe we'll try to get to that in class and derive it a little better. Same thing with this one. The result of this, I don't think is terribly important because I don't like to memorize formulas. So like this formula, not important to memorize, just as like these ones, angle sum and angle difference formulas, not important to memorize. But if you kind of understand why they exist and then derive them yourselves, that's kind of a good thing a student should do in terms of their mathematical understanding of the topics. So that's all that there kind of was in this section. So make sure you understand rotations and at least the flip across the x-axis, and then you know how to take compositions by multiplying. So if you rotate and then flip, or flip then rotate, know what order that's going to be done in, know how to compute the matrix multiplication based off of that. Excuse me. That is essentially what all the exercises from that section talk about. Then we got back into the more general theory of linear transformations. We got into one-to-one, onto. So remember, one-to-one also means injective. So I'll use the word injective. Surjective means onto. So you should know what these concepts are, what they mean, and then also know how to demonstrate them in basic cases, or at least justify why something is one-to-one, why it is not onto. So of course, this section and isomorphisms, let's see. So some of these, we've actually found easier ways. So given a linear transformation, determining whether it's one-to-one and onto. Sometimes you can determine those, whether or not it's invertible. So we talked about how taking the inverse of a matrix, if we can compute an inverse, it's going to be an isomorphism, and that isomorphisms are one-to-one and onto. If it's not invertible, we also talked about how the rank can determine the dimension of the kernel and the image. So these notions of one-to-one and onto tie in pretty heavily with the kernel and image. So some of the techniques we learned after this are almost a little bit more useful. So if we take a look at this section, a lot of the examples say, prove that it is not one-to-one, prove that it is one-to-one, show that it is onto or not onto. Pay attention, understand the techniques and arguments as to how to show that. But I would also recommend, understanding the concepts of kernel and image and some of the techniques we use there, because those same arguments can be made a lot quicker just by understanding properties of kernel and image. And we'll get to that in a second once we get to that section. Let's take a look at some of these examples and see what types of examples that come up. So typically, of course, we've got these linear transformations and we want to know, is it one-to-one? Is it onto? So being able to demonstrate that, again, you should be able to argue why something is one-to-one or onto. Whether you want to kind of try to compute it explicitly from the definitions of one-to-one or onto, you can. We can also use maybe some dimensionality arguments, right? So in this one, we've got T is going to transform a two-dimensional vector into a three-dimensional vector. And this one, actually, we got to be very careful because it just says is T one-to-one and onto, but it doesn't say what the domain and range is. So one key point, as we're getting into kernel and image, a linear transformation is always surjective onto its image. So it's always onto on the image. And we know now that the kernel and image form vector spaces themselves. So you kind of have to be careful. This is why we like to write these statements, like T from Rn to Rn. You kind of want to know what your full domain is and what space you're landing in. Because if you don't particularly define what space you're landing in, well, you can't really, you're not really clear on what we are onto or what we are surjecting onto or what we are questioning, whether it's surjective onto which image or what vector space. So I'll try to be careful with that with writing problems. Of course, since we're in this section, I think we want to assume that the linear transformation is from, for example, this one, it's from R2 to R3. So it's a good question. Is this going to surject onto R3? Likewise, this one, we've got a map from R3 onto R2. Will it be surjective from R3 to R2? Will it be injective? Will it be one-to-one from R3 into R2? So some of those questions you can answer instantly with an appropriate theorem, or just knowing why and being able to explain why, maybe by a dimensionality argument. Other ones you might need to do a little bit of work for. So all fairly basic questions. And it looks like there's a few more in this section. Let's take a look. Give an example of a 3x2 matrix as a linear transformation determined by this matrix that is one-to-one but not onto. That actually sounds like a pretty good question. That might be a good kind of quick question to take a look at. Of course, in any of these, there'll probably be a question somewhere along these lines of, given a matrix or given a linear transformation, asking whether it's injective, whether it's surjective, and justifying why it is or isn't. Some of these other ones that are a little more theoretical, I think these last three. Yeah, so like explaining why a matrix, n by n matrix, is both one-to-one and onto if it's rank n. Theorem, we kind of talked about that in class, but again, we didn't actually even in class, we didn't prove some of the theorems because we don't really have time for it. But I did try to at least explain, give you some understandings of the bigger concepts. You should kind of know those explanations and concepts, but I wouldn't ask you to regurgitate it, especially since it's not made rigorous. But you should know how to apply it. Right? So we know that if it's a square matrix and it's one-to-one and its rank is n, then it should be both one-to-one and onto. So those are other tools you can use in terms of justifying whether a matrix is one-to-one or onto. These other matrices, or the other examples, So some of these might make decent true false questions, right? Once it gets into like show or demonstrate, those make pretty decent true false questions. So maybe understand why it's true, or at least be able to justify it to yourself why it should be true or false. And then be careful with the statements, because I can always switch around some of the conditions of the statement. And if it makes it not true or not false based on the original one, you should kind of understand why. Isomorphisms. So we were mentioning earlier, of course, isomorphisms are invertible. That's going to be our key thing with these guys. So they are injective and surjective, and anything that is injective and surjective, we're going to be able to come up with an inverse. So really easy in terms of what we've learned so far, especially if at least if the domain and range, if we're mapping from Rn to Rn, pretty easy to determine the inverse of a matrix. We know how to do that. It's going to get a little trickier, and I'll probably put a question like this on the exam. Let's see. Isomorphisms map bases to bases. Good concept to know. There might be some true false questions based off of that. Let's see. Showing that two vector spaces are isomorphic. Might make a decent question. The other questions that get a little harder in this are going to be, I think, this problem and this problem. So now we're working with subvector spaces. So let's see, this one's not too bad. I think this one, we've just got a map from V to W, find the matrix of the isomorphism, and then we just know how the matrix should act on a collection of vectors. And since that collection of vectors was a basis, we can invert it and find that. Not a bad example. Something like that you guys should know how to do. Let's see, where was the example I was looking at? I'm pretty sure it was in the, oh no, it's in the next section. Okay. So this section, I guess, not too bad. Understanding how to find inverses of matrices. Most of these examples are fairly straightforward. Of course, any of these show it must be the case that something, you should understand why these are true. But again, I wouldn't ask you to write out the full proof of showing these types of things. So maybe a true false concept question based off of those. And a lot of these show questions. Any of the computations, coming up with the matrix of a linear transformation using this invertibility technique from these previous examples might show up. Let's see, what else do we got from this section? Looks like we got quite a bit, but I think a lot of these are a little proofy. Yeah. So some of these, if they get a little lengthy and they seem like a little proofy, hang on, let's see this question. Might be decent. This question is kind of similar to this question that comes up in the kernels and images. So let's talk about these guys. Kernels and images are the first example of subspaces that naturally come about from linear transformations. So you should be able to understand what a subspace is. It's going to be a vector space, but possibly generated by a skew set of vectors. So something that's like not the standard bases, or not even a subset from the standard bases. So kernels and images, you should know their definitions, know what they mean. And then you should be able to compute them. So compute bases for the kernel and image, and know how to go about doing that. So we've seen a few examples where we're just given an explicit computation for a linear transformation. Understand how to compute the kernel, understand how to compute the image. And then, of course, our big theorem from this section was the dimensionality, that the dimension of the kernel plus the dimension of the image has to be the dimension of our domain, right? Everything in the domain we can plug into a linear transformation, and it has to go somewhere. So it's either going to go to 0 or it's going to go to something that's not 0. That is kind of the heart of what's going on with this theorem. And then, of course, by the linearity of our transformations, of our spaces, it boils down to a nice dimensionality argument, or a nice dimensionality theorem. So some theorems here about the dimensions again might show up good at true-false questions. And then this question. I think I might put something like this on the midterm. I think this is actually where we're at. Actually, no, I'm not sure if we did this example in class. Maybe we'll go through something like this. So this one's important because, as I was mentioning earlier, a linear transformation is surjective onto its image. It's kind of a cheap little cop-out if you think about it. We may not hit all of the vectors in R3, but there is a set of vectors that we are guaranteed to hit. That is the image of T. That is the range of T. And since we know we hit all of them, that is, we are surjecting onto an image. So you should understand why that is. And then we also have this property that if we at least have an injective map, so injectivity now with kernels, we can simply show that the kernel is 0. So this might be an easier way to talk about injectivity, especially if we're given a matrix. We can compute the kernel of the matrix. And so if the kernel is 0, if we have a linear transformation that is injective, then it is necessarily, I guess I should say, if it's an injective map and the dimension of the target space is bigger than the domain, I guess that has to be the case. If it's an injective map, then it's automatically surjective onto its image. So it's both injective and surjective, meaning it's an isomorphism from its domain onto its image. And so there's a tricky thing we can do. Since it's an isomorphism onto its image, we can come up with an inverse, at least when we're restricted to that image. And so what we're doing here is we kind of show that the linear transformation, it maps the standard basis vectors into these two vectors. So we know 2 vectors in the image. We know that an isomorphism will map bases to bases. And so we know a basis for the image of T is going to be these 2 vectors, namely the column vectors. However, that vector space, the image, sits inside a higher dimensional vector space. It sits inside R3. So what you have to do is try to find another vector that is linearly independent from the 2 basis vectors that span the image that will give us an entire basis for R3. Once you have that, you can come up with a matrix A that will represent the inverse of T when restricted to the image. So pretty much one of the hardest things in this section. I kind of like this problem. I think it really ties in a lot of the concepts of kernels, images, and inverses all together, as well as these concepts from the last chapter. We mentioned how when we first started talking about bases, we mentioned how if I have a basis for a subvector space, a subspace, that we can always then extend that basis into a higher dimensional space. So if I have like a 2-dimensional vector space sitting inside a 4-dimensional vector space, whatever basis we have for that 2-dimensional vector space, we can always find 2 other vectors to add on to get a collection of 4 elements of our basis set now for the 4-dimensional space. So we can always build on smaller bases of subsets. So it ties into that as well. Here, once we look at the image, well, our image can only be 2 dimensions since that's all the domain was. And so we found these 2 vector spaces that are going to be basis elements for our image. And now what do we want to do? We want to expand that basis to a full basis of R3. So this is an extra vector that we throw in there. And now we have a basis for R3 building from the bases off of the image. And then from that, now we're computing the inverse. So it ties in a lot of concepts. It's a very good problem, very good thing to understand in terms of everything we've been doing this past week and a half. So take a look at that. I think I'll probably put one of those on the exam. And then let's see. So that'll be a big problem from this section. Of course, more practice with stuff like that are all going to be in these questions. These all look very standard, very computational, computing the dimension of the kernel, extending the basis from one to another is a good one. I should also mention finding the basis for the kernel is another good problem for these ones. Again, tying in these concepts of bases and subspaces, since these kernels and images, since I've said like they are the first really good examples of vector spaces and subspaces that we get from linear transformations, it's important to understand, you know, how they work, how they're modeled, how they behave along with the linear transformation. So for example, like in this problem here, I think we did this example in class as to coming up with a basis for the kernel. So the way we did it here, we simply essentially found a description of all of the vectors in the kernel and then come up with a span of that based off of vectors. That's probably one of the best ways to do it. There's probably some other ways using linear transformations, and especially if you have a matrix and then doing some row reduction properties. This ties way back into some of the things we were doing the first couple weeks, where if you find 0 rows in your reduced row echelon form, and you can use that, once you have a reduced row echelon form, you can determine which vectors are going to go to 0, and then based off of that, come up with a model like this and or a basis for that. So those are some good examples. Let's see. So we went over that, and then our last couple sections. So matrix of a linear transformation. This we went over a couple days ago. Biggest thing, change of bases. And now we know change of bases are isomorphisms. Big thing with the change of bases. Always remember, change of bases matrices don't actually they send a vector to itself. The vector starts as itself, ends as itself. It just looks different because we're changing our scales. We're changing our bases. So that kind of helps, for me at least, to keep straight which direction, which bases we're changing to and from. So, right, we're starting with a vector x. Now we're changing it to the same vector x in regards to a different basis b. We are looking at x and to the scalar, the linear combination that we can arrive at from b to get x. So understand the change of bases as well as these matrices here. How to represent a linear transformation in regards to a different set of bases. So definitely going to be a question like that. Most of these questions, I don't ever intend to put anything. I think the biggest matrices you'll ever have to look at are probably going to be 3x4. I think 4x4 is going to be too big. Even some 3x4, I think, are going to be big. There might be some skew matrices, and the biggest skew matrix might be a 3x4. But I will try to keep the computations required for a lot of these not too heavy, especially if there's, I mean, with the number of problems, I'll have to balance it out, like between the number of problems and the length of the computations. So some of these problems, like if you have to compute these vectors, these ones weren't too bad. You know, we showed what this in class. It was a 2x2 matrix though, and a 2x2 significantly easier than 3x3, of course. And so as long as you kind of understand this formula and understand our steps in class of how to compute a matrix in regards to a different bases. It's not too bad, right? It's all just a matter of matrix multiplication. Most of the time, the inverse change of basis is easy to come up with almost instantly because we're almost always starting with the standard bases. The t, the transformation, as long as we're acting on a standard basis, again, easy to come up with. And so it's like you have to kind of compute the inverse of one matrix. So understanding what to compute the inverse of, what order to put them in, and then just computing them, if you understand the process, shouldn't be too bad. Yeah, so this is just matrix of a transformation with regards to an arbitrary basis. I don't know. These steps might almost be overkill. The way we did it in class, as we saw, was just matrix multiplication is really what it boils down to. And then so today we want to talk about, let's see, so don't want to waste too much more time describing these. General solution to a linear system. Expect a problem like this on the exam, and we'll talk about what's going to come out of it. It's pretty basic, and if you look at the problem, so it'll make maybe more sense after we get through lecture here. But if you look at the problems, write the solution. We'll start off with like a linear transformation acting on a vector space. This is the homogeneous solution, and then this is the specific solution. So notice the matrix is the same, but now we're asked to find a specific solution to a vector. And so finding the general solution is just a matter of finding the solution. Really what we're looking for is the solution of the kernel. So this ties into finding the bases of the kernels, and then finding a specific solution, and then we can find the entire general solution based off of that. So these problems kind of work in pairs, like 1 and 2 are tied together, 3 and 4 are tied together, 5 and 6 tied together. All decent examples. This one, I mean, if you want to try it, go for it. I probably won't. I will for sure not give you guys a 4x4. I think that it'll just get too computationally intensive, and it's not going to illustrate whether or not you kind of know how to do it. That is the basis of this class, right? If you know how to do the problem solving methods, that's good enough. I would expect that if you had the time and if you had to solve a bigger system of linear equations, since you know how to do it, you could either compute it yourself or maybe try to program a computer, write a Python program or something to help you compute bigger solutions to bigger matrices and bigger systems of equations. And so that's it for this section, for this chapter. Again, kind of a lot of these are tied together, right? Like today, we're going to be using kernels a lot. So especially if some of these topics really bleed into each other, that'll help me kind of minimize the total number of problems you guys have to do. Any questions? All right. So let's finish off with that last topic. And let me see. So let me pull up my outline. I think we might have had one thing we were finishing with. Yeah, the little example I was saying I really liked that I don't think we've done yet. So let's see. I think this was from our kernel and image section. Yeah. So let's walk through this example. We've got a linear transformation from R2 into R3 given by T of X is 1, 1, 0 and 0, 0, 1 acting on X. So we know that then we can define a vector space V as the image of T, and that is a subspace of R3. So moreover, show that 1, kernel of T is equal to 0. 2, we want to argue, or at least explain, why T is an isomorphism. From R2 onto V. And this is why it's important to list the domain or the target space as well, because it's certainly not going to be an isomorphism from R2 all the way on to R3, but from R2 onto V, it will be an isomorphism. And then 3, we want to find T inverse from V to R2, specifically, so that is find the matrix A from R3 to R2 such that when A is restricted to V, A is an isomorphism, and represents T inverse. So our solution, so this is a little more written out than what the book does it. The book kind of jumps right into this last part, but I think understanding these first two parts are also important. So because we have a transformation from a lower dimensional space into a higher dimensional space, we want to be careful. It's not always the case that T is going to be an isomorphism onto its image. We need T to be injective first. So we need to show that the kernel of T is equal to 0. So why should the kernel of T equal to 0? So here's our matrix. Two ways. We want to show kernel of T is equal to 0. Any suggestions? There's two good ways to do this. We could do it explicitly. Well, actually here, I think both ways are going to reduce to the same thing. If we have an equation, we are looking for the set of vectors that maps to 0. And we want to show that this x vector is equal to the 0 vector. And so, of course, this is our x vector by shorthand without writing out the coordinates. Well, this is just a matter of finding the solution to a system of equations, namely what we would solve by our row reduction methods in terms of the augmented matrix. And so we could say by row reducing, what are we going to get? Easily get a row of zeros there, and then of course we get 0, 1. Of course the third one's all zeros. And then we can switch 2 of the rows to get our nice identity matrix, 2 by 2 sitting inside this 3 by 3. And then we switch the rows. So what does this mean? Actually, I'm kind of blending these methods together. This is essentially telling us that the rank of our matrix is 2, right? I have two rows with ones in it. Even though we have a 0 row, it's fine because we are only starting with a 2-dimensional space. So since the rank of t equals 2, which is the dimension of R2, of course, so the kernel of t equals 0. The other way we could do this is to simply multiply everything out. And if we did multiply everything out, I didn't even do this right. There shouldn't have been a z here. Excuse me. We're acting on a 2-dimensional vector, not a 3-dimensional vector. So that gives us a rank argument. You could also argue along these same lines from this matrix, or you probably could have started from the beginning and then just shown that what happens if we multiply that out, especially since the numbers weren't too bad. It's a case where even multiplying things out is actually the quicker method. If we multiplied it out, what would it show? It would have showed x equals 0, x equals 0, and y equals 0 would have been the 3 equations we got from multiplying, matrix multiplying our matrix on the vector. And so the equations, of course, we get x equals 0, y equals 0. This implies that the entire vector is itself 0. So again, the kernel of the transformation is just the 0 vector. And of course, then t is injective. Or 1-to-1 if you want to use that term. So 2, why should t be an isomorphism? We know t is injective. And then t is always surjective onto its image. That is essentially the definition of the image, right? The image is the set of all vectors that t will hit. So we know t hits everything in the image, which means it's surjective onto that. I don't really want to write that out mathematically. You should kind of understand why that's true. Fairly basic concept. So t is an isomorphism. So namely our R2 is going to be isomorphic to V. Our third step is kind of where the meat of the problem lies. So we know we want to extend t or we don't want to extend t, we want to find an inverse of t. So we know that t sends bases to a basis because it's an isomorphism. So t of E1, we know is going to be the first column, and t of E2 will give us the second column. And so this is kind of a nice result. There's some subtle things going on here. Namely that if we know that the matrix of a linear transformation, if we know that transformation is injective, then the columns are always going to be linearly independent, meaning the columns of that matrix that represents the transformation are always going to be a basis for the image. So it's a quick, easy thing to just write down, but a fairly deep concept here. So not a lot of problem solving we had to do for that part, but you really got to understand why and what's going on. So we know V is the span of those two, and since V is a subspace of R3, we can extend. Let's call just this set. Sorry, I'm gonna squeeze this in here. So just this set of two vectors, let's just call that our B for the basis. We can extend B to a basis of R3, i.e., we need one more vector that is linearly independent with B, with the vectors in B. So this is where it could get kind of tricky, depending on what these column vectors are. Most of the time it should be easy enough. And this is actually kind of a little bit of like free problem solving where answers are not necessarily going to be unique. Typically what you're going to want to do is find an easy vector. I would say check all of the standard basis elements and try to see if it's linearly independent from those two. Well, nicely enough, one of these, this is the standard basis E3. So we shouldn't check that. We don't want to add that same vector in there. And here I have 1, 1. So there's a lot of different choices that we could choose here. And a lot of different things we could do. Do you guys want me to follow the book, or maybe we could do a little bit different? Let's do a little different. I'll let you follow the book and check their solution. Maybe I'll explain a thought process I see when going about this, because as I was saying, it is a free solution in some sense. Like you have some freedom in your choice. It's not going to be unique. There's not necessarily a rigorous way of finding this third vector, because all you need is some vector that's linearly independent from the two you're given. And if you're given reasonably nice vectors, you know, the numbers aren't too big, they're not too crazy. It's not like 7, -35, and 15 on either of those. Usually you want to choose an easy vector, especially if we're going to compute the inverse from this set. But on the other hand, you could almost choose, there's a lot of different vectors you could choose that wouldn't be wrong. So my thoughts, if I were to see something like this, well, we know E3 is already taken care of. And this first vector, it points in the direction of E1, E2. So we have 1, 1. So maybe if we kind of ignore the third dimension, we've got nothing going on in the first two dimensions from this vector. And this vector is only 1, 1. What's a common way to find a different basis vector, or a vector that's perhaps orthogonal to 1, 1? Maybe we can choose, let's call it little u equal to something like 1 - 1. I know that this guy is going to be not in the span of this guy because they're orthogonal. And this guy's clearly not going to be in the span of this guy because it's, you know, they have zeros in the wrong coordinates. And so it should be fairly clear that if I take any linear combination of these guys, I'm never going to get this vector. Or, so someone mentioned in the chat, 0, 1, 0. Or even, I'm pretty sure you could probably choose 1, 0, 0. Would also work. So, which one you guys want to do? So if it all makes sense, hopefully it is. This one, for me, was kind of an easy choice because I know it's not going to be in the span of these two. These ones, you got to think a little bit. I know that, of course, this one and that one, they're never going to be in the same span, and the span of this guy or linear combinations of this E3 vector that we have are never going to result in, you know, getting another coordinate, a non-zero coordinate in the first or second coordinate. And then, of course, this one says that the first two have to be the same. And so as soon as I change one of those, we're going to be outside the span of this guy. And moreover, since the coordinates with which each of these vectors have zeros in, when I take a linear combination of vectors of these, it's always going to have something in the third coordinate, and then the first two coordinates have to be the same. So as soon as I introduce a vector where the first two coordinates are different and nothing in the third coordinate, it's not going to be in this span. Does that make sense? Moreover, well, how would we actually show that? How would we show that the vector we chose is actually linearly independent from these two? We would row reduce. And this does kind of lead into the next step. So not terribly important to check, or at least to prove that in your work, because we're going to be proving that in the next step. Maybe let's check this guy here. So let's call this guy U. Let's call this guy V. Let's call this guy W. So now we're going to choose W so that our set of vectors 1, 1, 0, 0, 0, 1, and 1, 0, 0 our claim is going to be that the span of this should be all of R3. I know that the first two are linearly independent, so that if this guy was somehow not linearly independent from the first, we're not actually going to span R3. And how would we show that? We would simply show that by our next process, namely by trying to compute the inverse. So if now A is the matrix of 1, 1, 0 and 0, 0, 1, it's kind of T, but now we're kind of appending this extra row. Then A inverse is going to be a map from R3. Wait a second, what am I doing? TA inverse. Hang on a second. What am I thinking? Right, we want to act that on the standard basis elements. So we're going to have so A is essentially embedding R2 in the R3. And so what we want to do is to come up with the inverse of A, but then we need to restrict the dimensions on that. Give me 1 second. Sorry, I'm getting lost in my own work here. Okay. We need to come up with an equation of where this guy is going to go. This 1, 0, 0. So we know here, let me ignore it, rewrite this real quick. So what's going on with this guy? We know that A inverse of 1, 1, 0 should be equal to 1, 0. We also know that A inverse of 0, 0, 1 should also equal 0, 1. This is simply because of the fact that we know that, right, A acting on 1, 0 should give us the first column. A acting on 0, 1 gave us the second column. The third column we kind of just threw in there, though. So the question is, where should A inverse of 1, 0, 0 go? So it can pretty much go anywhere. Right, I know that since we're mapping a 3-dimensional space onto a 2-dimensional space with this inverse matrix, and maybe I should relabel it. So we know that A, so this shouldn't be A. If A is our matrix representation of T, it's going to be 1, 1, 0 and 0, 0, 1. We're going to label it as A inverse, but of course it's only going to be invertible on the subspace. We can essentially send this vector to anything in R2. And so namely what we might want to send it to is just one of the other basis vectors, say to 1, 0. Since we know R2 is only spanned by 2-dimensional 2 vectors, and we already have basis vectors for our image that are mapping to the basis vectors of R2, well, the third basis vector in the set that we came up with, our basis for R3, it's going to map into the image. It's going to map into R2, namely as some scalar combination of the other 2 basis vectors. And we kind of have a choice of where we want to send that, since all we really need is these 2 conditions to hold. So what we're going to have is that A inverse acting on our 1, 1, 0, 0, 0, 1, and 1, 0, 0 is going to equal 1, 0, 0, 1, and 1, 0. And so how do we find this inverse? By matrix multiplication. So we need to compute the inverse of this guy here. For the sake of time, so since we don't have a whole lot of time left in class, I will leave that computation to you guys. But hopefully the ideas there make sense. There's kind of a lot going on, and we have this choice of our freedom. Not only do we have this choice of choosing this extra vector to span all of R3 to extend our basis from our image, but now when we're trying to come up with the inverse, or what would be the inverse of our transformation, or at least a transformation that restricts to the inverse when restricted to the image, we have an extra choice of, well, where should this extra basis element go? And so since we're mapping that back into R2, it doesn't quite matter. We can really send it back anywhere we want. And so picking an easy choice of where we're sending it is usually the easiest way to solve the problem. Of course, we could have chose 0, 1. We could have chose 1, 1. Any of those would have worked. Any questions on that problem? Okay, so sorry for taking up a bit of time. I did want to explain all of the problems and what would be on the exam, but unfortunately we are eating up a bit of time in terms of material. We want to talk about the matrix of a general solution. So that isn't going to be much different. Of course, finding the solution, as you can imagine, we'll have to be doing these row reductions. So our general solution to linear systems. So if we have a matrix system of equations, we've shown that we can kind of boil it down into a format of AX is equal to B, where A is usually the matrix representing some transformation. So just some basic definitions. So I guess we can write this for, or Tx equal to B. If we have a specific vector that satisfies equation 1, so both of these equations, whether we're considering it as a linear transformation or specifically getting into the matrix of that, then X is called a specific solution. I think the book might call it a particular solution. The general solution of equation 1 is given by this is a little bit different notation than what the book uses. So I'm just going to write it as X of P plus the kernel of T. And what do I mean by this? This is going to be the set of all vectors xp plus v and Rn for some vectors that are in the kernel. So keep in mind that the kernel of T is really just the solutions to tx equals 0. Or, of course, ax equals 0. So if v is in the kernel, then t of any particular solution, excuse me, if we add on from the particular solution any vector in the kernel, by the linearity of t, well, this guy's going to be 0. So adding on anything in the kernel, once we apply the linear transformation, it's essentially going to be killed off because it's part of the kernel. And so whatever initial solution or whatever specific solution we found will still map to the specific vector, to the specific solution. So, examples. Let's see, I think the book has a 3x4 example. I don't want to work through all of that. So let's do something like finding the solution to 113 minus 1 minus 2 minus 4 215 xyz equals 0. So we want to find the homogeneous solution and then find the specific solution to, or the general solution, I guess I should say, to the full equation. So the steps in this, sorry for not writing it all out, but it might say something like find the homogeneous solution. Or something like find the kernel. And then 2, find the general solution. And we're running out of time. So let's try to do our computations real quick. Of course, what does this boil down to? This boils down to row reduction. And I guess I should specify that it doesn't matter which order we do these in. We can find a specific solution first, then find the kernel, and then write the general solution. Or if we wanted to find the kernel first and then find a specific solution, then find the general solution. Let's start off with finding the specific one. So we've got 113 minus 1 minus 2, 4, and 215. We are going to append by our column of constants. And now we row reduce to try to find a specific solution. So our specific solution, let's keep the first row as it is. Let's subtract off that one from the second one. We're going to have a 0. We're going to have a minus 1. We're going to have a minus 1. And then we're going to have a 1 and a 1. So it's minus row 1 plus row 2. Then we are going to take minus 3 row 1 plus row 3, give us a 0. So that'll give us positive 3, negative 4, negative 1. That'll give us negative 6 plus 5 gives us a negative 1. And then, let's see. What was here? Negative 3 And 4 gives us a positive 1 again. Third row is going to disappear. Since it looks just like the second row. And then now we want to see, can we reduce anything out from the first two rows? We can do negative row 2 plus row 1. So we will get a 1, a 0. That'll be a positive, so that'll be a 3 there. And then a 0 here. And then a 0, minus 1, minus 1. That one stays the same. And we still have a row of zeros. So to find a specific solution, we want to rewrite this as our system of equations. So this is, remember, our x, our y, and our z. First line is going to say x plus 3z equals 0. Second line is going to say minus y minus z equals minus 1 or equals 1. And then the third one says essentially z can be anything. So we want to pick non-trivial solutions. So we don't want all zeros. Though it does look like, depending on the constants, we can pick z is equal to 0. So if we pick z is equal to 0, that's going to tell us that y is equal to negative 1 and x is equal to 0. So our specific solution, 0, minus 1, 0. And if we check that, so if we have 0, minus 1, 0, when we do the first row, first column, we'll get a minus 1 times 1 will give us a 1. Second row, second column, or second row times that column will give us a positive 2. And then, of course, we'll get that 4 as well. So 0, 1, 0, 0, minus 1, 0. Good specific solution. Now, to find the general solution, we want to go back to this equation and solve all of the vectors in the kernel. Now, the nice thing about this, so big hint, if we were to solve this equation, we would essentially be solving the same solution, same system we did, except this last row would be zeros, right? So if this is our specific, I don't think we'll have enough space to put this. Let me see if we can maybe put 2 pages next to each other. So here's our specific. Our kernel, well, what are we going to have? We're going to have the same transformation, but now sending a vector, we're looking for the vectors it sends to 0. How do we find this guy? We perform the exact same row operations. So what's going to happen when we perform the exact same row operations? The coefficient matrix is going to end up being the same. Right? We're still going to want to do the exact same process we did at eliminating the corresponding positions, getting it in reduced row echelon form. And actually here, let's make these positive. Maybe we should have done one more step here to make the x and the y and z positive to be officially in row reduced row echelon form. And that would have made that a negative. But what's going to happen to our third column here? No matter what we do, if I add minus 2 row 1 plus row 2 to 0, it's just going to be all zeros. Everyone see that? So these general solution problems, not as much work as you think. It's kind of the same thing we've been doing, coming up with the specific solution. Then to come up with the kernel, since you've already done all the row operations, it's not that much extra work because you don't have to go and redo all the row operations once you've done them. We know that if I reduce the transformation into reduced row echelon form, the process is going to be the same. And nicely enough, now if we append a row of zeros, all the row operations acting on a column of zeros is still going to give us zeros. Whether we're switching columns, multiplying multiples. And so once we have that, now we can try to come up with a basis for our solution, for our kernel. So here's how we might find a basis for our kernel. This system of equations says now x plus 3z equals 0 and y plus z equals 0. So the vectors in the kernel are going to be of the form minus 3z minus z and z. How many rows of zeros did we have in reduced row echelon form? One row of zeros. What is the rank of our matrix in reduced row echelon form? We have 2 non-zero rows. So the rank 2 plus the nullity is going to give us the total dimension, our 3 by 3, meaning our nullity, our null space, which is also another name for the kernel, should be one-dimensional. So here, our bases should only have one element. One vector will span the bases of our kernel. And all this is saying is we're looking at linear combinations, namely scalar multiples of this one vector. Sorry, I wrote basis for kernel there under that. And so our general solution now you simply write as your specific solution. Sorry, let's just write it as x is equal to 0 minus 1, 0, plus a linear or a scalar combination, linear combination of the basis vectors of your kernel. So you can write as minus 3, minus 1, 1. You could keep using a z if you want for your parameter. We've commonly used s's and t's. You can use s and t. Z is perfectly fine. Of course, this is a dummy parameter. And as long as you're not putting a vector line over it, it's fairly clear that it's a scalar. And so this is our general solution. Any questions on that? So again, not too bad. All these computations, hopefully you guys are getting used to. We are just kind of throwing them at you in different ways. These now kernels, these inverses, isomorphisms. A lot of these problems just come down to row reduction. But you got to make sure you're kind of setting them up right and understanding what you're setting it up and what they mean.